In this section, we are going to generalize what we have implemented in the previous section. And that means that we are now computing the context vector for all the other inputs. Previously, we have only done that with respect to the second input, using that as the query. Now we are going to generalize it so that we get the context vector also for all the other inputs. So how we are going to do that is by, just reusing the code that we have written before. So here I'm just instantiating a placeholder self-attention class, a PyTorch class, so that we can use this self-attention concept a bit more, I would say, compactly without having to manually have multiple Jupyter Notebook cells and so forth, which is very error prone. So we'll organize everything into one class. And then we are going to reuse the code that we have above here. So here, just going to take this one and put it here in our constructor. So this will initialize these weight matrices when we create a new object. I need a self here in addition. Okay. Next, what we're going to do is we need the attention score computation. So I had it right here. So we will put that in the forward, because this is what we instantiate, and then we are going to use it in the forward call here. So like this. Let's call it values. And then we do the same for the queries. Now we are going to do it for all the queries. Before we only did it for the second query. What is missing is the attention score and weight computation. So the attention scores here, it's right. Yeah. So, whoops, we put it right below here. And now it's with respect to the queries. Then we're going to reuse the softmax. Again, with respect to all the attention scores. Yep, and I think this is about it. Oh, the context vector computation, which we can copy from here. There we go. And this should be about it. So let's give it a try. Let's use our torch.manual seed 1, 2, 3. And then let's call that self-attention version 1, because I will show you a slightly improved version in a few moments. And we have to give it our input and output dimensions, which are used here to instantiate the weights. And then we can call this one on the input. So just maybe before I execute it, the inputs are our input embeddings. So the first token, second token, and so forth. So I'm calling it on our inputs here. And let's see what happens. So yeah, this gives us some values. And it works out nicely here that now we generalize that and we get the context vectors for each of the inputs. Just to double check that these numbers are correct, we know what this one should be. This is the second context vector, second row. So we know what that should be. So by the way, again, each one corresponds to one token. So this is, maybe just like this, it might be easier. So this one is the context vector using this as a query. This is the context vector using this as the query, and so forth. And yeah, this one should match, the second one should match what we have computed previously. So the second query as the second input as the query. And we can see this here is actually the same as this one. So our implementation here is correct. Now I wanted to show you a slightly better way of implementing this. So we can call this version 2. And so in PyTorch, there's a concept called the linear layer that is also used in multi-layer perceptrons, for example. And so what we can do is we can use, instead of creating these ourselves, we can take advantage of this torch.n.linear. And I shouldn't have removed those. We still need that. So we can actually also create this linear layer. It's just like a slightly simpler way. And this will create a linear layer that has a weight matrix, and it has a bias parameter. I can show it maybe here, just as an example. Torch.n.linear. Let's do a 2x3. And then you can see there is a weight matrix here. And there's also this bias tensor. We don't need the bias tensor. We just want a weight matrix. So what we do is we can set this to false. Bias false. And to make it maybe more general, we can call it QKV bias. Some LLMs use that and some LLMs don't use that. So it really depends on the implementation. It's more popular nowadays not to use it, but GPT-2, for example, originally used it. So it really depends on the LLM. It's not necessary to use it. So modern LLMs don't use it anymore. So that's why I'm setting it to false here. Okay. So now we have those. So it's a slight modification. We replaced our manual parameter generation with this linear, so we don't have to call torch random. And the initialization here of the initial weights, it's also slightly more optimal, these values. So there's a weight initialization scheme that takes into account the dimensions here and so forth. So it usually results in better training dynamics if we just use this in a linear layer compared to using our torch random here, which we haven't normalized. So these are just small random values, and here there's a slightly better weight initialization under the hood, basically. So we're taking advantage of that. Now, this changes only slightly. So how this changes is that now we have these, and they are called like this, where we have the inputs as the input and so forth. So I can copy it down here. And the rest should be the same. Let me just update it. Values. And this should be it. Let's double check if everything works. But don't expect the exact same results as above here. That's because the weight initialization here is different. So we have different initial weights, and that is why you won't notice the same values. I think the reason is I called them key and value instead of keys and values. Yeah. So yeah, this works. But the values look a bit funny. They're a bit large. I mean, they would be optimized during the training, but we can also just, use a different random seed, get smaller values, which look a bit better. But this is something that would get optimized during the neural network training. And yeah, so in this section, we generalized our computation to generate the context vectors for all the other inputs. In addition, we also have this nice compact self-attention class now that uses the linear layers and that we can use.
Get this book at Manning.com.